Gas inside galaxies remains in constant motion. In star-forming disks, diffuse material drifts between dense clouds, heats under radiation, cools through atomic emission, and responds to pressure gradients that evolve over millions of years. When energy injection persists in the same regions for long enough, gas develops a bulk flow. That flow moves away from the galactic midplane and into the surrounding halo, carrying mass, momentum, and thermal energy outward on scales far larger than any single star-forming region. This sustained motion defines a galactic wind. Galactic winds arise from cumulative processes rather than brief events. They grow from steady energy input distributed across space and time. Star formation concentrates power into limited volumes. Radiation, stellar winds, supernova shocks, and relativistic particles continuously deposit energy into the interstellar medium. As pressure builds, gas responds by expanding. Over long periods, this expansion organizes into coherent outflows that persist for tens to hundreds of millions of years. From a dynamical perspective, galactic winds reflect a balance between gravity and pressure. Galaxies contain deep gravitational wells formed by stars and dark matter. Gas remains bound as long as cooling and confinement dominate. When energy input raises gas temperature and pressure faster than gravity can respond, material begins to rise. Density gradients within disks guide this motion. Gas density decreases rapidly with height above the midplane, allowing pressure-driven expansion to proceed most efficiently perpendicular to the disk. The physics resembles atmospheric escape on a planetary scale, extended to entire galaxies. Heated gas expands upward, accelerates along pressure gradients, and entrains surrounding material as it flows. Continuous replenishment from below sustains the outflow. Once established, the wind becomes a long-lived feature of the galaxy's structure rather than a transient disturbance. Early observational clues emerged from spectroscopy. Star-forming galaxies display absorption lines shifted toward shorter wavelengths, indicating gas moving toward the observer at high speed. These velocities often reach several hundred kilometers per second, several hundred miles per second, exceeding typical rotational motion within disks. Emission line maps reveal extended structures rising above galactic planes, aligned with regions of intense star formation. Together, these signatures point to large-scale outflows driven internally. Galactic winds differ fundamentally from narrow jets. Jets originate near compact objects and propagate along tightly collimated paths. Winds arise across extended regions and fill wide, solid angles. Their structure reflects the distribution of star formation, the geometry of galactic disks, and the properties of surrounding halos. Bipolar flows dominate in disk galaxies, while more spherical outflows appear in compact starburst systems. Energy injection begins with massive stars. Radiation pressure acts immediately after formation. Ultraviolet photons ionize surrounding gas, heating it and increasing pressure. Stellar winds accelerate charged particles outward at thousands of kilometers per second, injecting momentum continuously. These processes inflate cavities in the interstellar medium, reducing density and allowing subsequent energy input to propagate more efficiently. Supernova explosions add impulsive energy on top of this steady background. In clustered environments, supernova remnants overlap and merge. Their combined shocks inflate superbubbles filled with hot plasma, reaching temperatures of millions of degrees. Sound speeds inside these regions become high, and pressure gradients smooth out rapidly. When superbubbles expand into the stratified disk, they elongate vertically and vent material into the halo. Once hot gas reaches the halo, it accelerates further. Thermal pressure, cosmic ray pressure, and magnetic stresses all contribute. Hot plasma flows outward, dragging cooler material along through turbulence and ram pressure. This entrainment produces a multi-phase wind composed of hot, X-ray emitting gas, warm ionized filaments, neutral atomic clouds, cold molecular clumps, and dust grains embedded throughout the flow. Each phase responds differently to forces. Hot gas provides most of the energy and velocity. Cooler gas carries most of the mass. Dust influences how radiation couples to matter. Magnetic fields thread through all components, guiding charged particles and shaping large-scale structure. The result is a complex, evolving system rather than a uniform stream. Galactic winds operate over long timescales. Individual massive stars contribute for a few million years. Star clusters contribute for tens of millions. Sustained star formation maintains outflows for far longer. Over these periods, winds can remove substantial fractions of a galaxy's gas reservoir, especially in low-mass systems with weaker gravity. In massive galaxies, winds often lift gas into extended halos, where it remains bound and later cools and returns. This circulation plays a central role in galaxy evolution. Winds regulate star formation by limiting how quickly gas converts into stars. They prevent excessive central concentration of baryonic matter. They shape disk thickness, influence spiral structure, and maintain turbulent support within the interstellar medium. Simulations that include realistic winds reproduce observed galaxy masses, sizes, and star formation histories more accurately than those that exclude them. Galactic winds also mediate the exchange between galaxies and their environments. Gas flowing outward enriches the surrounding circumgalactic medium with heavy elements forged in stellar interiors. Carbon, oxygen, silicon, and iron spread far beyond their birthplaces. These elements later participate in cooling, star formation, and planet formation elsewhere. In this way, winds connect local stellar processes to cosmic chemical evolution. Supermassive black holes add another source of sustained energy. Accretion onto a central black hole converts gravitational potential energy into radiation and mechanical power with high efficiency. When this energy couples to surrounding gas, it drives fast, massive outflows that propagate through the host galaxy. These black hole-driven winds interact with stellar winds, sometimes reinforcing them, sometimes dominating the flow, depending on accretion rate and galactic structure. Despite their diverse origins, all galactic winds share a common foundation. They emerge from continuous energy input into gas embedded within a gravitational potential. They persist through steady driving rather than brief disruption. They transport matter and energy across vast distances, reshaping galaxies gradually over cosmic time. Gas enters galaxies along large-scale filaments, cools, forms stars, absorbs energy, and then flows outward again. Within this cycle, galactic winds function as the primary pathway through which galaxies respond to their own activity, redistributing material, regulating growth, and maintaining a dynamic equilibrium that unfolds across hundreds of millions of years. Inside giant molecular clouds, gravity concentrates gas into dense knots embedded within turbulent flows. These clouds span tens to hundreds of light years and contain enough mass to form thousands of stars. Temperatures remain low, often just a few tens of Kelvin above absolute zero, allowing molecules to survive and radiative cooling to remain efficient. Within this environment, local instabilities amplify. Gas compresses along filaments. Angular momentum builds. Protostellar cores form and accrete rapidly from their surroundings. Among these newborn objects, massive stars stand out almost immediately. Their growth accelerates quickly, drawing in large amounts of material before radiation feedback becomes dominant. Once nuclear fusion ignites in their cores, energy output rises steeply. Luminosity increases roughly as the cube of stellar mass, meaning a single massive star can emit more energy than thousands of smaller ones combined. This energy couples to surrounding gas from the earliest moments of stellar life. Ultraviolet radiation emerges as the first major influence. Photons with energies above the ionization threshold of hydrogen propagate into nearby gas and strip electrons from atoms. neutral hydrogen transforms into ionized plasma, and gas temperature rises to around 10,000 degrees Celsius, roughly 18,000 degrees Fahrenheit. Pressure inside this ionized region exceeds that of the surrounding cold molecular cloud by orders of magnitude. As pressure equalizes, ionized gas expands outward. The expanding front drives a shock into the surrounding neutral medium, sweeping gas into dense shells. These structures grow over time, forming nearly spherical cavities centered on the massive star or star cluster. Their expansion speed depends on gas density, radiation intensity, and the geometry of the surrounding cloud. In dense environments, growth proceeds slowly but steadily. In lower density regions, ionized gas advances more rapidly, carving extended channels through the cloud. These ionized bubbles alter star formation almost immediately. Gas compressed into expanding shells can fragment and collapse, producing secondary generations of stars. Elsewhere, material disperses and becomes too diffuse to collapse further. Massive stars therefore regulate star formation on local scales by redistributing density rather than simply heating gas uniformly. Radiation also transfers momentum directly to matter. Photons carry momentum proportional to their energy, and when absorbed or scattered by dust grains embedded in gas, they impart a continuous outward push. In regions with abundant dust, radiation pressure becomes dynamically important. Dust grains absorb ultraviolet photons, heat up, and re-emit energy at infrared wavelengths. Those infrared photons scatter repeatedly within dusty environments, multiplying the momentum transferred to gas. This effect intensifies in regions of clustered star formation. When many massive stars form close together, radiation fields overlap. Dust becomes optically thick at infrared wavelengths, trapping energy and enhancing pressure. Over time, this process clears low-density cavities and opens preferential pathways through which gas and radiation escape. At the same time, massive stars launch stellar winds. These winds arise from the interaction between intense radiation fields and ions in the stellar atmosphere. Photons transfer momentum to atomic absorption lines, accelerating charged particles outward. Wind velocities commonly exceed 1,000 kilometers per second, several hundred miles per second, and mass loss rates increase sharply with stellar mass and metallicity. Stellar winds inject both momentum and energy continuously. Over a few million years, a single massive star can deposit kinetic energy comparable to that released by a supernova. In star clusters containing dozens or hundreds of massive stars, winds collide and merge, creating collective outflows that reshape their surroundings on scales far larger than any individual star. Where winds interact with ambient gas, shock fronts form. Gas compresses and heats as shocks propagate outward. Behind these shocks, wind material accumulates into hot, low-density plasma. Temperatures reach millions of degrees, and cooling times become long. These regions inflate steadily, forming wind-blown bubbles bounded by expanding shells of swept-up gas. Magnetic fields influence this expansion from the beginning. Galactic magnetic fields thread molecular clouds and ionized regions alike. As ionized gas expands, it stretches and reorients magnetic field lines. Magnetic pressure resists compression in some directions, while allowing expansion in others, producing anisotropic growth. Observations reveal elongated cavities and filamentary shells shaped by the combined influence of gas pressure and magnetic tension. Cosmic rays begin contributing even before the first supernova. Shocks generated by stellar winds accelerate particles to relativistic energies. These particles diffuse rapidly through surrounding gas, exerting pressure over large volumes. Unlike thermal gas, cosmic rays remain energetic even as gas density decreases, allowing them to influence regions far beyond the immediate vicinity of massive stars. Together, radiation pressure, stellar winds, magnetic fields, and cosmic rays act continuously on star-forming regions. Their combined effect reorganizes gas distribution, lowers average density near massive stars, and increases porosity within molecular clouds. Dense clumps resist acceleration and remain embedded, while diffuse material responds quickly and moves outward. As multiple massive stars form within the same cloud, their individual feedback zones overlap. Ionized regions merge, wind bubbles connect, pressure equilibrates across tens to hundreds of light years. These merged structures evolve into superbubbles, extended cavities filled with hot plasma, bounded by shells of cooler gas and dust. Superbubbles grow over millions of years. Inside them, sound speeds become high, and pressure gradients smooth rapidly. Gas responds coherently rather than locally. When superbubbles encounter the vertical density gradient of a galactic disk, expansion accelerates upward. Density decreases with height, offering less resistance to pressure-driven motion. Bubbles elongate and stretch into chimney-like structures that connect star-forming regions to the galactic halo. This vertical coupling represents a critical transition. Energy injected on stellar scales begins influencing galactic-scale gas flows. Hot plasma escapes into the halo, carrying with it momentum and thermal energy. Cooler gas entrained along the bubble walls follows more slowly, forming filamentary structures that trace the flow. Observations across the electromagnetic spectrum capture these early stages clearly. Optical emission reveals glowing ionized shells surrounding massive stars. Infrared observations trace warm dust heated by intense radiation fields. X-ray measurements detect hot plasma filling superbubbles. Radio observations map magnetic field orientations and cosmic ray interactions. Each wavelength probes a different component of the same physical system. By the time the first supernova occurs, the environment around massive stars has already changed dramatically. Gas density near the stars has dropped, cavities have opened, pressure gradients align preferentially upward. When supernova shockwaves arrive, they propagate through an environment shaped for large-scale expansion rather than confinement. This preconditioning enhances the effectiveness of explosive feedback. Supernova energy couples efficiently to hot, low-density gas. Shockwaves travel farther, overlap more easily, and deposit energy across broader regions. Instead of dissipating locally, energy contributes to coherent motion that feeds developing outflows. Simulations that include early stellar feedback reproduce these behaviors consistently. When radiation pressure, stellar winds, magnetic fields, and cosmic rays operate from the onset of star formation, energy injection spreads smoothly across time. Outflows develop gradually rather than erupting abruptly. The transition from local turbulence to organized galactic winds appears continuous. Massive stars therefore influence galaxies long before they die. From the moment fusion begins, they inject energy and momentum into their surroundings, reshape density structures, regulate star formation, and establish pathways for gas to move outward. Each photon emitted and each particle accelerated contributes incrementally to a larger pattern of motion that links stellar birth to the slow, sustained breathing of galaxies. Massive stars evolve quickly. After only a few million years, nuclear fuel in their cores rearranges into heavier elements, fusion pathways shift, and internal balance changes. Pressure support weakens, cores contract, temperatures climb sharply. When fusion can no longer counter gravity, collapse accelerates inward at a significant fraction of the speed of light. In less than a second, the core rebounds, launching an outward shock that tears through the star's outer layers. This marks the onset of a supernova. In isolation, a supernova represents an intense but localized event. A single explosion releases about 10 to the 51 ergs of energy, briefly outshining an entire galaxy. A shock wave expands outward, heating and compressing surrounding gas, sweeping up material into an expanding shell. Over tens of thousands of years, the remnant slows, cools, and merges with the surrounding interstellar medium. In clustered star-forming environments, supernovae rarely occur alone. Massive stars tend to form together in associations and clusters drawn from the same molecular cloud. Their lifetimes span a narrow range, set primarily by mass. As a result, supernovae occur in sequences rather than isolation. One explosion follows another within the same region, separated by tens of thousands to a few 100,000 years. On galactic timescales, these intervals are short. When a second supernova detonates inside the expanding cavity of a previous one, the outcome changes dramatically. The shock propagates through hot, low-density gas rather than dense molecular material. Energy loss through radiation drops sharply. The shock travels farther, faster, and with greater coherence. Momentum accumulates rather than dissipating locally. As multiple supernovae overlap in space and time, their remnants merge into a collective structure. Individual shells dissolve into a larger volume of hot plasma. Temperatures remain at several million degrees. Pressure stays high. Cooling times lengthen. This merged region evolves into a superbubble. Superbubbles represent a transition from stellar-scale feedback to collective galactic influence. Their interiors behave differently from isolated remnants. Sound speeds are high, allowing pressure to equilibrate across large volumes. Turbulence mixes freshly injected energy rapidly. Instead of fragmented shocks, the system responds as a unified structure. Each additional supernova injects energy into an environment already primed to transmit it efficiently. Momentum adds constructively. Thermal energy accumulates. The superbubble expands steadily, sweeping surrounding gas into a thick shell. The shell grows denser as it incorporates ambient material, while the interior remains hot and rarefied. The geometry of galactic disks strongly influences this expansion. Gas density decreases with height above the midplane. Gravitational restoring force weakens in the vertical direction. As a superbubble grows, expansion proceeds more rapidly upward than sideways. The structure elongates, stretching into a chimney-like form. Once the expanding shell reaches a critical height, structural integrity weakens. Rayleigh-Taylor instabilities develop as dense shell material accelerates above lighter interior gas. Fingers of hot plasma push through gaps. The shell fragments. Hot gas vents into the galactic halo. This venting phase marks a qualitative shift. Energy that once circulated within the disk begins coupling directly to large-scale outflows. Hot plasma accelerates along pressure gradients into lower density regions. Additional supernovae continue feeding the flow from below, sustaining it over extended periods. At this stage, the distinction between a superbubble and a galactic wind begins to blur. Supernova-driven outflows possess a strongly multiphase character. Hot gas from the interior expands rapidly, forming the fastest component of the flow. Cooler gas from fragmented shells becomes entrained, accelerating more slowly. Dense clumps stretch into filaments under shear and turbulence. Dust grains embedded within these structures travel alongside gas, tracing the outflow geometry. Momentum transfer plays a central role. Expanding hot gas exerts ram pressure on cooler material. Turbulent mixing layers form at interfaces between phases. Gas ablates from cloud surfaces and joins the flow. Over time, mass loading increases as more material becomes incorporated into the outflow. Magnetic fields thread through this entire system. As expanding plasma moves outward, it drags magnetic field lines with it. Field amplification occurs through compression and shear. Magnetic tension resists fragmentation in some regions while channeling flow in others. The resulting structure often exhibits coherent filamentary features aligned with magnetic field geometry. Cosmic rays contribute additional pressure. Supernova shocks accelerate particles to relativistic energies with high efficiency. These particles diffuse through superbubble interiors and into surrounding gas. Because cosmic rays interact weakly with matter, they propagate over large distances while maintaining pressure. Their presence smooths pressure gradients and sustains outflows even as thermal gas cools. In starburst environments, where supernova rates rise dramatically, these processes intensify. Hundreds or thousands of explosions can occur within a few million years in compact regions. Energy injection becomes nearly continuous. Superbubbles grow rapidly and break out early. Outflows reach velocities of hundreds to over 1,000 kilometers per second, hundreds of miles per second, extending far into galactic halos. The collective nature of supernova feedback explains why isolated explosions rarely drive galaxy-scale winds on their own. Dense interstellar gas absorbs energy efficiently when shocks propagate alone. Radiative cooling drains thermal energy before significant mass can escape. Clustering changes this balance by maintaining low densities and high pressures over large volumes. Numerical simulations demonstrate this effect clearly. Models that distribute supernovae randomly throughout a disk produce weak, fragmented turbulence. Models that cluster explosions reproduce large superbubbles, vertical chimneys, and sustained outflows. Energy coupling efficiency increases by orders of magnitude when explosions overlap. Timing also matters. Early stellar feedback from radiation and winds reduces gas density before the first supernova occurs. This preconditioning allows supernova energy to propagate efficiently. Shock waves expand faster, overlap more readily, and contribute directly to coherent motion. Stellar birth and stellar death therefore operate as a continuous sequence rather than separate phases. As supernova-driven outflows develop, they interact with gas inflows from the surrounding halo. Hot gas rising from the disk meets cooler material, accreting along large-scale filaments. Shear mixing and cooling occur at these interfaces. Some gas slows and eventually returns to the disk. Some accelerates further and escapes into the circumgalactic medium. The fate of outflowing gas depends on galaxy mass and structure. In low-mass galaxies, escape velocities remain modest. A significant fraction of supernova-driven material reaches intergalactic space. In massive galaxies, gravity confines much of the flow to extended halos, where gas cools over long timescales and participates in circulation rather than permanent loss. Regardless of outcome, collective supernova feedback reshapes the interstellar medium. Gas distribution becomes porous. Large cavities connect star-forming regions across the disk. Turbulence sustains pressure support against collapse. Star formation slows and spreads over longer timescales. Observational evidence reflects this picture. X-ray observations reveal extended hot gas halos above star-forming disks. Optical and ultraviolet spectroscopy detect fast-moving ionized gas associated with supernova-driven outflows. Radio observations trace synchrotron emission from cosmic rays accelerated by overlapping shocks. Together, these signatures point to sustained collective processes rather than isolated explosions. Supernovae therefore function as amplifiers rather than initiators. Their power emerges most clearly when combined, structured by environment and sustained over time. Each explosion adds energy to a system already in motion, reinforcing pressure gradients and extending the reach of outflows. Within star-forming galaxies, clustered supernovae transform localized stellar death into a collective force, driving gas upward, linking stellar evolution to galactic-scale circulation, and sustaining the long-lived outflows that carry energy and matter far beyond the regions where the stars themselves were born. Galactic winds carry material in many physical states at once. Close to their origin, temperatures span an enormous range, from gas-heated to millions of degrees, to dense clouds that remain only a few tens of Kelvin above absolute zero. Despite these differences, all of this material participates in the same large-scale outward motion, responding to shared pressure gradients, turbulence, and momentum transfer. At the heart of every galactic wind lies hot plasma. This component forms when supernova shocks and stellar winds thermalize their energy in low-density regions. temperatures reach several million degrees Celsius, millions of degrees Fahrenheit, stripping atoms of most or all of their electrons. At these temperatures, gas emits primarily in X-rays and becomes nearly invisible at optical wavelengths. Hot plasma provides the engine of the wind. Its thermal pressure drives expansion. Sound speeds exceed hundreds of kilometers per second, allowing pressure imbalances to smooth out rapidly. Gravity exerts only a weak influence on this component. Once established, hot gas accelerates outward naturally, flowing along the steepest pressure gradients and expanding into the surrounding halo. Embedded within this hot flow lies warm ionized gas. This material typically maintains temperatures near 10,000 degrees Celsius, around 18,000 degrees Fahrenheit. It consists of hydrogen and heavier elements ionized by radiation and shocks, emitting characteristic optical and ultraviolet emission lines. Observationally, this phase appears as filaments, arcs, and diffuse halos extending above galactic disks. Warm, ionized gas forms through several pathways. Some originates in ionized shells around superbubbles that fragment during breakout. Some condenses from cooling hot plasma as it expands. Some consists of pre-existing interstellar gas swept up and accelerated by the wind. Regardless of origin, this phase traces the interaction between fast, tenuous plasma and denser material. Cooler still is neutral atomic gas. This phase includes hydrogen atoms that remain unionized, typically at temperatures of a few hundred to a few thousand degrees. Neutral gas often appears in absorption against background starlight or in emission at radio wavelengths. In galactic winds, neutral gas travels more slowly than hot plasma, but carries a significant fraction of the total mass. The coldest component consists of molecular gas. These clouds contain molecules such as molecular hydrogen and carbon monoxide and represent the raw material for star formation. Temperatures often remain below 100 Kelvin. Their presence within galactic winds initially surprised astronomers. Dense molecular clouds seem fragile compared to the violent environment of a hot outflow. Observations now reveal molecular gas moving outward at high speeds in many galaxies. This gas appears clumpy and filamentary, often embedded within warmer material. Its survival depends on shielding, rapid cooling, and continual replenishment from denser regions. Rather than existing as intact clouds lifted wholesale, molecular gas likely forms and reforms within the wind itself through compression and cooling. Dust accompanies all these phases. Dust grains form in stellar atmospheres and supernova ejecta and consist of silicates, carbon compounds, and other refractory materials. Although dust contributes little mass, it plays a critical role in wind dynamics. Dust absorbs and scatters radiation, transferring momentum from light to gas. It also catalyzes molecule formation and influences cooling rates. The coexistence of such different phases raises a central question. How do they remain coupled? The answer lies in momentum, transfer, and turbulence. Hot plasma expands rapidly, exerting ram pressure on embedded clouds. As fast-moving gas flows past denser material, shear develops at interfaces. Kelvin-Helmholtz instabilities arise, mixing hot and cool gas. At the same time, thermal conduction transfers heat across boundaries, while radiative cooling counteracts heating in denser regions. These competing processes create turbulent mixing layers around cool clouds. Gas ablates from cloud surfaces, joining the hot flow. At the same time, compressed regions within the wind cool efficiently, allowing new cool gas to condense. The wind therefore maintains a dynamic equilibrium in which material continuously transitions between phases. Magnetic fields strongly influence this interaction. Field lines thread through both hot and cool gas, coupling their motion. Magnetic tension suppresses some instabilities and enhances others, altering how clouds fragment and survive. In many cases, magnetic fields wrap around dense clumps, insulating them partially from thermal conduction and extending their lifetimes. Cosmic rays add another layer of coupling. These relativistic particles stream along magnetic field lines, exerting pressure over large volumes. Because cosmic rays interact weakly with matter, they influence both dense and diffuse gas nearly equally. Their pressure gradient contributes to lifting material out of the disk and sustaining motion even where thermal pressure declines. The result is a wind that behaves less like a simple flow and more like a turbulent ecosystem. Hot gas accelerates fastest and sets the overall structure. Warm and cool gas respond more slowly but remain dynamically linked through drag, turbulence, and magnetic forces. Dust traces these interactions, revealing how radiation couples to matter across phases. Each phase occupies a characteristic region of the wind. Hot plasma fills most of the volume, forming the background through which other components move. Warm ionized gas outlines interfaces and filaments, marking regions of active mixing. Neutral and molecular gas concentrate in clumps and elongated structures, often aligned with the direction of flow. Velocity measurements reflect this stratification. Hot gas reaches the highest speeds, often exceeding several hundred kilometers per second. Warm ionized gas moves more slowly, but still achieves substantial velocities. Cold molecular gas typically travels at the lowest speeds, though still fast enough to escape star-forming regions and rise into galactic halos. Mass distribution shows the opposite trend. Hot gas carries most of the energy, but little mass. Cold and warm phases carry most of the mass, but less energy per unit mass. This division shapes the impact of winds on galaxies. Energy transport regulates dynamics, while mass transport determines how much material leaves the disk. Cooling plays a central role throughout the flow. As gas expands, density drops and radiative losses change. Hot gas cools inefficiently at low density, allowing it to persist. Warm gas cools more efficiently, especially where metal content remains high. Cold gas cools rapidly when compressed, enabling molecule formation even within an outflow. This cooling hierarchy allows galactic winds to remain multi-phase over long distances. Instead of homogenizing into a single temperature, the flow continually generates structure. New cool gas forms, even as old clouds dissolve. Observations detect molecular gas tens of thousands of light-years from galactic disks, embedded within hot halos. The multi-phase nature of winds influences their ultimate fate. Hot gas often escapes into intergalactic space, carrying energy and metals far from the galaxy. Cooler gas more frequently slows, stalls, and returns under gravity, participating in galactic fountains. Dust grains survive long enough to seed surrounding environments before fragmenting or sputtering away. Numerical simulations reproduce these behaviors when they resolve small-scale mixing and include magnetic fields and cosmic rays. Simplified models that treat winds as single-temperature flows fail to match observations. Realistic winds require continual phase exchange and feedback between components. From a galactic perspective, multi-phase winds regulate star formation with precision. Removing only hot gas would change little. Removing cold gas too efficiently would shut star formation down rapidly. By lifting gas into halos and allowing it to cool and return, winds stretch star formation over billions of years rather than consuming gas in short bursts. Chemical transport also depends on multi-phase structure. Heavy elements produced in stars distribute unevenly among phases. Some remain locked in dust grains, some dissolve into hot plasma, some cycle repeatedly between phases before escaping or returning. This complex mixing sets the chemical evolution of galaxies and their surroundings. Viewed as a whole, galactic winds resemble turbulent circulatory systems rather than uniform streams. Different phases move together, not because they share the same physical properties, but because they remain dynamically coupled through pressure, turbulence, magnetic fields, and radiation. Hot plasma drives, cooler gas responds, dust mediates, cosmic rays smooth and sustain. Within this layered flow, matter constantly changes state, shape, and trajectory. Yet the collective motion persists. Gas rises, mixes, cools, condenses, and accelerates again, forming a living outflow that links stellar processes deep inside galaxies to the vast, diffuse environments that surround them. Starburst galaxies concentrate star formation into compact regions with extraordinary intensity. Gas surface densities rise sharply. Star formation rates climb to tens or hundreds of solar masses per year, within regions only a few thousand light-years across. Under these conditions, energy injection into the interstellar medium accelerates dramatically, and the balance between gravity and pressure shifts across the entire galaxy. In these environments, galactic winds transition from secondary features to dominant dynamical agents. Starbursts often begin when gas accumulates rapidly. Galaxy mergers, close encounters, or strong tidal interactions drive gas inward toward galactic centers. Angular momentum redistributes, gas compresses, densities increase, cooling accelerates. Within a short span of cosmic time, massive star clusters form in large numbers, tightly packed and overlapping in space. The consequences follow quickly. Radiation fields intensify across entire central regions. Stellar winds overlap almost immediately. Supernova rates increase by orders of magnitude compared to quiescent disks. Energy injection becomes nearly continuous, maintaining high pressure throughout the starburst zone rather than in isolated pockets. Under these conditions, pressure rivals gravity on galactic scales. The gravitational potential of a galaxy depends on stellar mass, gas mass, and the surrounding dark matter halo. In normal disk galaxies, gravity confines most gas efficiently. In starbursts, sustained energy injection raises thermal, turbulent, magnetic, and cosmic ray pressure throughout the central regions. Gas responds collectively, not locally. Large volumes begin expanding together. Observations reveal this transition clearly. Starburst galaxies display broad emission lines, indicating gas moving at several hundred to over 1,000 kilometers per second. Absorption lines trace outflowing material across wide angles rather than narrow cones. X-ray observations show extended halos of hot plasma enveloping starburst cores. These signatures indicate winds powered by distributed feedback rather than isolated sources. One defining feature of starburst-driven winds lies in their mass loading. As hot plasma expands, it entrains large quantities of surrounding gas. Turbulence, instabilities, and cloud ablation pull cooler material into the flow. In starbursts, the amount of gas lifted into motion often exceeds the mass converted into stars. This ratio, known as the mass loading factor, rises dramatically compared to normal galaxies. High mass loading alters wind dynamics. Carrying more mass reduces terminal velocity but increases the impact on galactic gas reservoirs. Winds become efficient at removing star-forming material from disks. Dense clouds lift, fragment, and stretch into filaments. Some gas accelerates beyond escape velocity and leaves the galaxy entirely. The geometry of starburst winds reflects the structure of their host galaxies. In disk-dominated systems, outflows emerge preferentially along the minor axis, forming large-scale bipolar structures. In compact or irregular starbursts, winds expand more isotropically, enveloping the galaxy in an outflowing cocoon. Classic nearby examples illustrate these behaviors. The galaxy M82 exhibits a spectacular bipolar wind extending tens of thousands of light-years above its disk. Optical filaments trace warm ionized gas. X-ray emission reveals hot plasma filling the outflow. Molecular gas observations detect cold material moving outward alongside hotter components. Together, these phases demonstrate how starbursts mobilize entire interstellar media. Starburst winds influence disk structure directly. Sustained pressure inflates disks vertically, increasing scale height and turbulence. Gas becomes more diffuse. Spiral structure weakens. Star formation spreads over larger volumes rather than remaining confined to thin layers. In extreme cases, disks partially evacuate, leaving central cavities dominated by hot gas. At the same time, winds interact strongly with surrounding halos. As outflows propagate outward, they encounter circumgalactic gas accreting from the cosmic web. Shocks form at interfaces, mixing layers develop. Some inflowing material heats and joins the outflow. Some cools and rains back toward the galaxy. These interactions regulate how much fresh gas reaches the disk during a starburst episode. Chemical enrichment accelerates dramatically in this regime. Starbursts produce heavy elements at high rates. Winds transport these elements efficiently into halos and intergalactic space. Observations detect metal-enriched gas far beyond starburst galaxies, indicating large-scale redistribution of stellar products. This process shapes the chemical evolution of galaxy groups and clusters. Starburst winds also influence future star formation indirectly. By removing or redistributing gas, they limit how long intense star formation can continue. Gas depletion times shorten. Eventually, star formation slows as fuel becomes scarce or too dispersed to collapse efficiently. In this way, winds contribute to the self-regulation of starbursts. Cosmic rays play an enhanced role in these environments. High supernova rates inject large populations of relativistic particles. These particles diffuse through dense starburst regions and into surrounding halos, exerting pressure comparable to thermal gas. Cosmic ray-driven winds develop smoother acceleration profiles, lifting gas gently over large distances rather than through abrupt shocks alone. Magnetic fields strengthen during starbursts as turbulence amplifies field lines. Stronger fields couple gas across phases, guiding outflows and stabilizing filaments. Synchrotron emission observed in radio wavelengths traces these fields and reveals coherent structures extending far from galactic disks. The competition between gravity and wind pressure depends strongly on galaxy mass. In low-mass starburst galaxies, escape velocities remain modest. Winds readily eject gas into intergalactic space, removing a large fraction of the galaxy's baryonic content. In massive starbursts, deeper gravitational wells confine more material. Gas rises into extended halos, circulates, and eventually returns. This mass dependence introduces diversity into galaxy evolution. Low-mass galaxies experience strong, irreversible mass loss during starbursts, limiting their future growth. Massive galaxies experience cycles of intense activity followed by recovery as gas fountains replenish disks over time. Numerical simulations capture this transition vividly. When star formation rates cross a critical threshold, winds shift from localized disturbances to galaxy-wide flows. Pressure-driven expansion overwhelms disk confinement. Outflows accelerate and remain coherent over large distances. Simulated galaxies develop extended metal-rich halos and reduced central gas densities consistent with observations. Starburst winds also interact with black hole activity. In some systems, rapid star formation coincides with increased accretion onto central supermassive black holes. Stellar-driven winds and black hole-driven outflows intersect, shock, and merge. The combined feedback enhances gas removal and reshapes central regions efficiently. Timescales remain central to this process. Starbursts last tens to hundreds of millions of years. Winds operate continuously throughout this period. Even after star formation declines, outflows persist as stored energy continues driving expansion. The imprint of a starburst therefore extends far beyond its active phase. From an energetic standpoint, starbursts convert gravitational potential energy of infalling gas into kinetic and thermal energy of winds with high efficiency. Energy that might otherwise deepen gravitational wells instead powers outflows that redistribute matter across cosmic environments. Viewed across cosmic time, starburst galaxies represent periods when galactic winds reach peak influence. They mark episodes when feedback reshapes structure rapidly, regulates growth forcefully, and exports matter and energy far beyond galactic boundaries. In these extreme systems, winds no longer act as background regulators. They become defining forces, rivaling gravity itself, altering disks, sculpting halos, and sending enriched gas into intergalactic space as a direct consequence of concentrated, sustained star formation. Galaxies contain more than stars and gas. Threaded through their disks and halos lie magnetic fields, faint in strength yet vast in extent, woven into nearly every phase of the interstellar medium. Along these fields travel cosmic rays, relativistic particles accelerated to near light speed by shocks and turbulence. Together, magnetic fields and cosmic rays provide a form of pressure that behaves very differently from thermal gas, and their influence becomes increasingly important as galactic winds develop and propagate. Magnetic fields in galaxies typically measure a few microgauss in strength, comparable in energy density to thermal gas, turbulence, and cosmic rays. Although weak by everyday standards, these fields fill enormous volumes and remain dynamically relevant because charged particles cannot easily cross them. Instead, plasma and cosmic rays tend to move along magnetic field lines, tying their motion to large-scale galactic structure. In star-forming disks, magnetic fields are amplified by turbulence. Supernova explosions, stellar winds, and differential rotation stretch and twist field lines, increasing magnetic energy through dynamo processes. As star formation intensifies, so does magnetic field strength. In starburst regions, magnetic energy density can rival or exceed thermal pressure, altering how gas responds to feedback. Magnetic pressure contributes directly to lifting gas. As hot plasma expands upward from star-forming regions, it drags magnetic field lines with it. Field lines resist compression and bending, storing energy in tension. This magnetic tension redirects motion, guiding gas preferentially along certain paths and stabilizing structures against fragmentation. Rather than expanding isotropically, winds develop coherent filamentary channels shaped in part by magnetic geometry. Cosmic rays add another critical component. These particles originate primarily in supernova shocks, where diffusive shock acceleration transfers energy from expanding shock fronts to charged particles. A significant fraction of supernova energy enters the cosmic ray population. Once accelerated, cosmic rays diffuse rapidly along magnetic field lines, spreading energy far beyond the immediate explosion site. Unlike thermal gas, cosmic rays lose energy slowly. Their cooling times often exceed hundreds of millions of years. As a result, cosmic ray pressure persists even as hot gas cools and expands. This long-lived pressure acts over large distances, contributing to sustained acceleration of outflows well beyond the star-forming disk. Cosmic rays interact with gas through scattering off magnetic irregularities. As they stream outward along field lines, they excite small-scale waves that transfer momentum to the surrounding plasma. This process couples cosmic rays to gas motion, allowing relativistic particles to push matter outward despite their negligible mass. The combined effect resembles a distributed pressure gradient rather than a localized force. Gas experiences a gentle but persistent upward acceleration. This mechanism contrasts with purely thermal driving, which relies on steep pressure gradients near energy injection sites. Cosmic ray-driven acceleration remains effective even in regions of low density and low temperature. This distinction becomes important in the outer regions of galactic winds. As hot gas expands into the halo, it cools adiabatically. Thermal pressure declines. In purely thermal winds, acceleration weakens and flow can stall. With cosmic rays present, pressure remains significant, allowing winds to continue accelerating or maintain velocity over tens of thousands of light years. Magnetic fields ensure that this pressure acts coherently. Field lines channel cosmic ray transport, aligning acceleration with large-scale outflow geometry. In many galaxies, magnetic fields bend from disk-parallel orientations into vertical or radial configurations above star-forming regions, naturally guiding winds into bipolar structures. Observations support this picture. Radio synchrotron emission traces cosmic rays spiraling along magnetic field lines, revealing extended halos around star-forming galaxies. Polarization measurements show ordered magnetic fields extending far above galactic disks, aligned with observed outflows. These structures indicate that magnetic fields and cosmic rays remain dynamically coupled to winds over large distances. Magnetic fields also influence how different gas phases remain connected. Dense clouds embedded within hot plasma experience magnetic draping, where field lines wrap around cloud surfaces. This draping suppresses some instabilities and reduces heat conduction, extending cloud lifetimes within winds. As a result, cold and warm gas survives longer while being accelerated upward. Cosmic rays penetrate dense regions efficiently. Because they interact weakly with matter, they provide pressure support even where thermal gas struggles to couple. This property allows cosmic rays to help lift cold and neutral gas that would otherwise resist acceleration. Observations of cold gas far from galactic disks align with models that include cosmic ray pressure. In low-mass galaxies, these effects become especially important. Gravitational potentials remain shallow, and cosmic ray pressure can rival or exceed gravity over large volumes. In such systems, cosmic ray-driven winds efficiently remove gas, contributing to long-term mass loss and suppressed star formation. In more massive galaxies, cosmic rays often support fountain-like circulation. Gas lifts into extended halos, slows under gravity, cools, and eventually returns. Even in these cases, cosmic rays extend the reach of winds and increase the volume of gas involved in circulation. Numerical simulations highlight the role of these components. Models that include only thermal feedback produce winds that cool too rapidly and fragment excessively. When magnetic fields and cosmic rays are included, outflows become smoother, more extended, and longer-lived. Acceleration profiles match observed velocity gradients more closely, especially at large distances from disks. Timescales further emphasize their importance. Thermal pressure responds quickly but fades quickly. Magnetic fields evolve more slowly. Cosmic rays persist longest. Together, they provide a layered driving mechanism. Thermal pressure launches winds, magnetic fields guide them, and cosmic rays sustain them. This layered structure helps explain why galactic winds remain coherent over vast distances. Gas does not simply erupt and disperse. It accelerates, flows, and maintains direction, supported by invisible components that carry energy efficiently across space. From a broader perspective, magnetic fields and cosmic rays connect small-scale stellar processes to galaxy-wide dynamics. Supernova shocks accelerate particles locally, turbulence amplifies fields regionally, cosmic rays diffuse globally. The resulting pressure gradients shape outflows that extend far beyond their points of origin. In this way, magnetic fields and cosmic rays transform galactic winds from short-lived thermal expansions into persistent, large-scale circulatory flows. They lift gas gently yet relentlessly, sustain motion where other forces weaken, and help galaxies breathe over distances measured not in parsecs but in tens of thousands of light years. At the centers of most galaxies lies a compact object with a mass millions to billions of times greater than the Sun. Gas orbiting this object accelerates to extreme speeds, heats through friction and compression, and releases vast amounts of energy before crossing the event horizon. Even when the inflowing mass is modest, the energy liberated during accretion rivals or exceeds the combined output of all the stars in the host galaxy. This process powers an active galactic nucleus. As gas spirals inward toward a supermassive black hole, angular momentum forces it into a rotating accretion disk. gravitational potential energy converts efficiently into heat and radiation. Temperatures in the inner disk rise to millions of degrees. Intense ultraviolet and X-ray emission floods the surrounding region, interacting immediately with nearby gas and dust. Radiation pressure becomes enormous. Photons transfer momentum to electrons and dust grains, pushing material outward from the nucleus. When luminosity approaches a critical threshold known as the Eddington limit, radiation pressure rivals gravitational attraction. Gas hovering near the black hole experiences strong outward acceleration, initiating fast nuclear-scale winds. These winds emerge from regions only light days to light years across, yet they carry extraordinary power. Velocities commonly reach thousands of kilometers per second, sometimes exceeding 10,000 kilometers per second. Compared to stellar-driven winds, these outflows originate deeper in the gravitational potential and launch with far greater energy per unit mass. In addition to radiation pressure, magnetic fields play a central role near accreting black holes. Strong magnetic fields thread the accretion disk and twist under differential rotation. Magnetic tension extracts angular momentum from the disk, allowing gas to fall inward while simultaneously launching magnetically driven outflows. These winds carry mass, momentum, and energy away from the nucleus along wide angles. Some black holes also produce relativistic jets, narrow beams of plasma travelling near the speed of light. While jets differ from winds in geometry and composition, they interact strongly with surrounding gas. Shocks form as jets collide with interstellar material, inflating cavities and driving additional outflows. In many galaxies, jets and winds operate together, reinforcing large-scale feedback. As black hole-driven winds propagate outward, they encounter gas shaped by stellar feedback. Star formation has already carved cavities, reduced densities, and established pressure gradients. This preconditioning allows black hole winds to couple efficiently to the galactic interstellar medium rather than escaping freely. When fast nuclear winds collide with surrounding gas, shock fronts form. Kinetic energy converts into thermal energy. Gas heats to tens of millions of degrees. Pressure rises sharply. These shocked regions expand outward, sweeping up interstellar material and driving secondary outflows on kiloparsec scales. This two-stage process proves essential. The initial wind originates near the black hole with high speed but relatively low mass. Interaction with the galaxy transfers energy to a much larger mass of gas. Momentum multiplies. The resulting large-scale outflow slows compared to the nuclear wind but carries vastly more material. Observations reveal this structure clearly. X-ray spectroscopy detects fast, highly ionized winds close to galactic centers. Optical and infrared observations trace slower, massive outflows extending thousands of light-years from nuclei. Molecular gas observations reveal cold material entrained within these flows, indicating efficient coupling across phases. The impact on galaxies becomes profound. Black hole-driven winds inject enough energy to alter gas distribution across entire disks. Gas density drops in central regions. Star formation slows or halts as fuel disperses or heats beyond collapse thresholds. In extreme cases, galaxies transition rapidly from star-forming to quiescent states. This regulation operates through timescales matched to galaxy evolution. Accretion episodes last millions to tens of millions of years. Winds persist throughout these phases and often continue after accretion declines, driven by stored thermal and magnetic energy. The effects imprint themselves long after the nucleus dims. The relationship between black hole mass and galactic properties reflects this connection. Observations show tight correlations between black hole mass and stellar velocity dispersion, bulge mass, and central density. These correlations suggest coevolution regulated by feedback rather than independent growth. In massive galaxies, black hole feedback becomes increasingly dominant. Stellar winds struggle to expel gas from deep gravitational potentials. Black hole-driven outflows, with their higher launch energies, succeed where stellar processes alone remain insufficient. These winds heat halos, prevent gas from cooling efficiently, and suppress renewed star formation over long periods. In galaxy clusters, this effect scales further. Central galaxies host enormous black holes whose outflows inflate cavities in surrounding hot gas. X-ray observations reveal bubbles rising through cluster atmospheres, transporting energy outward and preventing catastrophic cooling. These same physical principles govern smaller galactic winds, extended to larger environments. The interaction between stellar-driven and black hole-driven winds varies with time. During early phases of rapid star formation, stellar feedback dominates. As gas funnels inward and accretion intensifies, black hole feedback strengthens. Winds merge, overlap, and reinforce each other, creating complex outflow structures shaped by both processes. Numerical simulations capture this interplay. Models that include only stellar feedback overproduce stars in massive galaxies. Models that include only black hole feedback suppress star formation too abruptly. When both operate together, galaxies evolve along realistic tracks, forming stars early, regulating growth, and transitioning gradually. Momentum transfer lies at the core of this regulation. Black hole winds deliver large momentum fluxes into galactic gas. Even when energy radiates away, momentum remains conserved, continuing to drive expansion. This ensures feedback effectiveness even under conditions of efficient cooling. The geometry of black hole-driven winds also matters. Wide-angle winds couple efficiently to disks. Collimated jets deposit energy at larger radii, but still influence central gas through shocks and turbulence. The diversity of outflow shapes produces a range of evolutionary outcomes across galaxies. As gas lifts and disperses, star formation adjusts accordingly. Some gas escapes entirely, some circulates through halos and returns later. Some remains heated and stable against collapse. Through these pathways, black hole feedback regulates not only how much gas galaxies lose, but how and when they form stars. Supermassive black holes therefore act as central regulators within galactic ecosystems. By converting accreted mass into powerful outflows, they influence gas on scales millions of times larger than their event horizons. Their winds dwarf stellar outflows in energy and reach, shaping disks, halos, and star formation histories across cosmic time. Within galactic winds, black hole activity adds a decisive layer of control, linking the smallest gravitational scales to the largest flows of matter and energy that galaxies sustain. Gas lifted by galactic winds follows different trajectories depending on how much energy and momentum it gains. Some material rises, slows, cools, and returns to the disk. Other material accelerates beyond the gravitational reach of the galaxy and joins the surrounding halo permanently. These two outcomes, circulation and escape, define the distinction between galactic fountains and galactic escapes. Both processes begin the same way. Energy injected by stars or black holes raises gas pressure in star-forming regions. Gas expands upward along density gradients, moving away from the galactic midplane. As it rises, gravity acts continuously, decelerating the flow. The eventual fate depends on the balance between upward momentum and gravitational pull. Galactic fountains describe flows in which gas remains gravitationally bound. In these systems, outflowing material reaches heights of a few to tens of thousands of light years before slowing. As pressure support weakens, gravity reasserts control. Gas cools radiatively, increases in density, and begins falling back toward the disk. This circulation resembles a hydrological cycle on galactic scales. Gas rises hot and diffuse, cools at altitude, condenses, and returns colder and denser. The timescale for a full fountain cycle typically spans tens to hundreds of millions of years, depending on galaxy mass and wind strength. Observations of nearby galaxies reveal fountain activity clearly. Neutral hydrogen clouds appear above disks, moving at velocities inconsistent with simple rotation. Some clouds show upward motion, others downward. Their metallicity often matches that of the disk, indicating recent ejection rather than pristine infall. These features trace gas in mid-cycle. Hot gas plays a key role in driving fountains. X-ray observations detect extended halos of hot plasma above star-forming disks. This gas provides pressure support at altitude, slowing the fall of cooler material and shaping its return paths. As hot gas cools slowly, it maintains the fountain structure over long periods. Cooling efficiency strongly influences fountain behavior. Gas enriched with heavy elements cools more rapidly than primordial gas. As winds carry metals upward, cooling becomes more effective at higher altitudes. Condensation occurs. Cool clouds form out of the hot phase and begin descending, often along filamentary paths shaped by magnetic fields and turbulence. Magnetic fields guide returning gas. Field lines stretched during outflow bend and reconnect as material slows. Gas tends to follow these structures back toward the disk, producing coherent inflow streams rather than random rain. This guided return redistributes gas across the disk, often depositing it far from its point of origin. Galactic escapes represent the opposite outcome. In these cases, gas reaches or exceeds the escape velocity of the galaxy. Gravity cannot reclaim it. The gas continues outward, joining the circumgalactic medium, or escaping into intergalactic space entirely. Escape becomes more likely when winds achieve high velocities, maintain pressure support over long distances, or act in galaxies with shallow gravitational potentials. Low-mass galaxies experience escape more readily. Their escape velocities remain low, and sustained winds can remove a large fraction of their gas. In massive galaxies, escape requires additional mechanisms. Thermal pressure alone often proves insufficient. Cosmic rays and magnetic fields extend acceleration beyond the disk. Black hole-driven winds deliver high initial velocities. Starburst conditions raise mass loading and momentum flux. When these effects combine, even massive galaxies lose gas permanently. Observational signatures distinguish escaping gas from fountain material. Escaping gas often exhibits higher velocities and lower densities. It remains hot or ionized over large distances. Absorption line studies detect metal-enriched gas far from galaxies, moving at speeds inconsistent with bound orbits. These features indicate material in transit to the circumgalactic medium. The circumgalactic medium acts as a reservoir for escaped gas. It contains material expelled by winds mixed with gas accreted from the cosmic web. Temperatures span a wide range from hot, diffuse plasma to cooler clumps. Escaped gas enriches this environment chemically, altering cooling rates and future accretion behavior. The distinction between fountain and escape shapes galaxy evolution profoundly. Fountain flows recycle gas efficiently. They delay star formation without removing fuel permanently. Gas returns altered in temperature, turbulence, and chemical composition. This recycling maintains star formation over long periods. Escape removes fuel outright. Repeated episodes reduce the total gas reservoir. Star formation declines. In low-mass galaxies, escape-driven loss can dominate evolution, producing gas-poor systems with limited future growth. Energy partitioning determines which outcome dominates. Winds that transfer most energy into thermal motion favour fountains as hot gas cools and stalls. Winds that transfer momentum efficiently favour escape, as momentum remains conserved even when energy radiates away. Cosmic rays and radiation pressure enhance momentum-driven behaviour. Geometry also matters. Gas escaping along low-density channels accelerates more effectively. Gas interacting with dense clouds loses momentum through mixing and cooling, favouring return. Galactic structure therefore influences outcomes on local scales even within the same system. Time dependence adds further complexity. Early in a starburst, winds strengthen rapidly and may drive escape. As gas depletes and star formation declines, winds weaken and fountains dominate. Black hole activity can reverse this sequence by injecting energy later, reopening escape pathways. Simulations reproduce these dual behaviors when they resolve halo structure and include multiphase physics. Gas follows diverse trajectories simultaneously. Some parcels escape, others circulate. The galaxy evolves through the combined effect of both processes rather than a single dominant mode. Metallicity patterns provide strong constraints. Disk metallicities reflect the balance between loss and return. Efficient fountains retain metals locally. Efficient escape lowers metallicity and enriches halos. Observed metallicity gradients across galaxies encode the history of these flows. Over cosmic time, galaxies experience repeated episodes of both fountain circulation and escape. Gas cycles multiple times before either settling into long-term equilibrium or leaving permanently. The relative importance shifts with mass, environment, and activity level. Galactic winds, therefore, do not produce a single outcome. They generate a spectrum of fates. Some gas rains back, sustaining star formation and internal regulation. Some gas departs, altering mass, structure, and chemical evolution far beyond the galaxy itself. Within this balance lies the long-term breathing pattern of galaxies, a circulation shaped by gravity and pressure, where every parcel of gas carries the memory of how far it rose, how long it lingered, and whether gravity ultimately called it home. Heavy elements originate inside stars. Nuclear fusion in stellar cores builds carbon from helium, oxygen from carbon, and progressively heavier elements in the most massive stars. Supernova explosions and stellar winds release these products into surrounding gas, enriching the interstellar medium with each generation of stars. From there, galactic winds take over as the primary transport mechanism, carrying these elements far beyond their birthplaces. This outward transport defines chemical enrichment on cosmic scales. Within star-forming regions, enrichment begins locally. Massive stars shed metal-rich material through stellar winds even before they explode. Supernovae then inject freshly synthesized elements directly into surrounding gas at high temperature and velocity. Initially, this material mixes with nearby interstellar gas, raising metallicity locally and influencing subsequent star formation. Without large-scale transport, this enrichment would remain confined to galactic disks. Galactic winds change that outcome. As hot plasma expands and accelerates, it entrains enriched gas and carries it upward into galactic halos. Metals that formed deep inside stars begin traveling distances thousands to tens of thousands of light-years away from their origin. The efficiency of this process depends on how metals partition among wind phases. Hot plasma contains newly synthesized elements in ionized form, mixed rapidly through turbulence. Warm ionized gas carries metals that cool from the hot phase or originate in swept-up shells. Dust grains lock metals into solid form, embedding them within colder gas. Molecular clouds carry metals that have already cooled and condensed. Each carrier behaves differently, yet all contribute to enrichment. Hot gas transports metals fastest and farthest. Cooler gas carries a larger fraction of metal mass, but moves more slowly. Dust shields elements from destruction and enables transport in dense clumps that survive long journeys. Observations reveal this distribution clearly. X-ray spectra of galactic halos show emission lines from oxygen, neon, magnesium, silicon, and iron, indicating metal-rich hot gas extending far beyond disks. Ultraviolet absorption studies detect enriched gas along lines of sight to distant background sources. Infrared observations trace dust expelled into halos and intergalactic space. These measurements demonstrate that galactic winds operate as efficient conveyors of heavy elements. Once metals enter galactic halos, they influence cooling behavior dramatically. Metal atoms provide numerous electronic transitions that radiate energy efficiently. Enriched gas cools faster than primordial gas, composed only of hydrogen and helium. This enhanced cooling promotes condensation, cloud formation, and eventual return flows in fountain-like circulation. Some enriched gas, however, escapes entirely. In low-mass galaxies, winds eject metals into intergalactic space efficiently. Over cosmic time, repeated episodes of star formation and outflow strip these galaxies of heavy elements. This explains why dwarf galaxies often exhibit low metallicity despite ongoing star formation. In more massive galaxies, metals accumulate in extended halos. These reservoirs remain gravitationally bound but displaced from star-forming regions. Over long timescales, cooling and accretion return enriched gas to disks, contributing to chemical homogenization across galaxies. The enrichment of intergalactic space provides one of the strongest pieces of evidence for long-lived galactic winds. Quasar absorption line studies reveal metal lines in regions far removed from any galaxy. Carbon, oxygen, and silicon appear in diffuse gas billions of light-years from major star-forming centers. These metals could only arrive there through sustained outflows. This process began early in cosmic history. Young galaxies formed stars rapidly and drove powerful winds. Even modest star formation rates in small galaxies contributed significantly to early enrichment because escape velocities remained low. As a result, the intergalactic medium acquired metals surprisingly early, within the first billion years after the Big Bang. Chemical enrichment influences structure formation itself. Metal-enriched gas cools more efficiently, allowing smaller structures to collapse and form stars. This feedback loop accelerates galaxy formation in enriched regions while leaving pristine regions less active. Galactic winds therefore introduce spatial variation into cosmic evolution. Dust transport adds further complexity. Dust grains survive long enough to travel into halos and beyond. These grains provide surfaces for molecule formation, especially molecular hydrogen. When dust-enriched gas later accretes onto galaxies, it promotes rapid cooling and star formation. Winds thus precondition future star-forming material chemically and physically. Iron provides a particularly informative tracer. Produced primarily in supernovae, iron abundance reflects the cumulative history of star formation and feedback. Observations show iron distributed broadly throughout halos and clusters of galaxies. This widespread presence indicates that winds operated efficiently over long timescales, repeatedly redistributing material outward. Galaxy clusters illustrate enrichment on the largest scales. Hot gas-filling clusters contains heavy elements at substantial levels. Because stars reside inside galaxies rather than in the intracluster medium, this enrichment requires extensive transport. Galactic winds, enhanced by interactions and black hole feedback, provide the mechanism. Chemical signatures also encode timing. Elements produced by short-lived massive stars appear earlier than those produced by longer-lived progenitors. The relative abundance of alpha elements compared to iron traces the sequence of enrichment events. Winds preserve these signatures as they transport material outward, allowing observers to reconstruct star formation histories across cosmic environments. Within galaxies, enrichment shapes internal evolution. Metal-rich gas cools efficiently, fragmenting into smaller clouds and forming stars more readily. Metal-poor gas remains warmer and more diffuse. Winds redistribute metals unevenly, flattening gradients and promoting mixing. Over time, this leads to more uniform chemical composition across disks. At the same time, repeated metal loss through winds limits runaway enrichment. Removing metals reduces cooling efficiency locally, slowing star formation and stabilizing disks. This balance between enrichment and removal maintains a long-term equilibrium in many galaxies. The connection between chemical enrichment and life emerges naturally from this process. Elements essential for rocky planets and biological chemistry form in stars. Winds transport these elements across galaxies and into interstellar clouds that later collapse into new planetary systems. Without large-scale redistribution, heavy elements would remain concentrated near their birthplaces. Each generation of stars therefore inherits material processed by earlier ones, carried across vast distances by galactic winds. Carbon atoms forged in ancient supernovae become part of interstellar molecules. Oxygen atoms cool collapsing clouds. Iron atoms seed planetary cores. The spatial reach of winds determines how widely these building blocks spread. Simulations confirm that realistic chemical evolution requires winds. Models without strong outflows trap metals too efficiently, producing galaxies with overly steep gradients and insufficient enrichment of halos. Including winds spreads metals broadly, matching observed distributions across environments. Chemical enrichment through winds remains ongoing. Even in the present universe, star-forming galaxies continue exporting metals into their surroundings. Halos grow richer. Intergalactic gas evolves chemically. Future star formation inherits an increasingly processed medium shaped by countless cycles of stellar birth, death, and outward flow. Through this process, galactic winds act as the universe's distribution network for heavy elements, linking stellar interiors to distant clouds, shaping the chemistry of galaxies, and quietly setting the conditions under which stars, planets, and complex structures continue to form. Young galaxies formed in a universe that looked very different from the one we see today. Gas densities were higher. Typical galaxies were smaller and more compact. Star formation proceeded rapidly, often in short, intense bursts. Under these conditions, galactic winds emerged early and operated with unusual strength, shaping both individual galaxies and the large-scale structure of the universe. In the early universe, gas flowed efficiently along filaments of the cosmic web. Gravity drew pristine hydrogen and helium into growing dark matter halos. Cooling proceeded quickly, allowing gas to collapse and ignite star formation soon after galaxies assembled. Massive stars formed in abundance, and their short lifetimes ensured rapid feedback. These first generations of stars injected energy into environments with shallow gravitational potentials. Young galaxies often contained far less mass than present-day spirals or ellipticals. Escape velocities remained modest. When stellar feedback began, gas responded dramatically. Outflows launched easily and propagated far from their host galaxies. Star formation rates relative to galaxy mass were high. Even small systems converted gas into stars rapidly. Radiation pressure, stellar winds, and clustered supernovae overlapped almost immediately. The distinction between localized feedback and galaxy-wide winds blurred early on, as energy injection affected entire systems rather than confined regions. As a result, early galactic winds achieved high mass loading. Large fractions of available gas entered outflows. Hot plasma expanded rapidly into surrounding space, dragging cooler material along. In many low-mass galaxies, winds removed more gas than remained available for future star formation. This behavior strongly influenced early galaxy growth. Repeated episodes of star formation followed by strong winds prevented runaway collapse. Galaxies grew in a punctuated manner, forming stars in bursts separated by periods of gas loss and recovery. This bursty growth pattern appears consistently in simulations of early galaxy formation. Early winds also played a central role in chemical enrichment. The first stars produced heavy elements efficiently, and winds transported these elements far beyond their birthplaces. Even modest galaxies contributed to enriching the intergalactic medium. By the time the universe was only a few billion years old, diffuse gas between galaxies already contained measurable amounts of carbon, oxygen, and silicon. This widespread enrichment altered the thermal evolution of the cosmic web itself. Metal-enriched gas cooled more efficiently, changing how filaments fragmented and how gas accreted onto galaxies. Regions exposed to early winds evolved differently from more isolated regions, introducing environmental variation into galaxy formation. Early winds interacted directly with the cosmic web. As outflows expanded, they collided with inflowing filaments. Shocks formed at these interfaces, some inflowing gas heated and mixed with outflows, some compressed and cooled, enhancing later accretion. These interactions redistributed momentum and energy across scales far larger than individual galaxies. Radiative backgrounds amplified these effects. Intense ultraviolet radiation from early star-forming galaxies ionized surrounding gas, contributing to cosmic reionization. Winds carried ionized, heated material outward, increasing the volume affected by stellar radiation. Together, radiation and winds transformed the state of baryonic matter across large regions. Reionization itself influenced wind behavior. Ionized gas remained hotter and more diffuse, reducing resistance to outflows. Winds traveled farther and remained effective for longer durations. The coupling between feedback and the ionized intergalactic medium strengthened early galactic influence on cosmic structure. Black hole activity also emerged early. Even modest black holes accreting at high rates produced powerful winds relative to their host galaxy mass. In compact early systems, black hole-driven outflows could dominate feedback temporarily, clearing central regions and suppressing star formation until gas reaccreted. The cumulative effect of these processes shaped the population of early galaxies. Many low-mass systems lost significant gas permanently. This loss limited their growth and contributed to the abundance of small, faint galaxies observed at later times. More massive systems retained gas more effectively, growing into the ancestors of modern large galaxies. Observational evidence supports this picture. Spectra of distant galaxies show strong outflow signatures even at high redshift. Absorption lines indicate fast-moving gas around young galaxies. Quasar sightlines reveal metal-enriched gas far from any visible galaxy, tracing early wind activity. Simulations of cosmic dawn reproduce these patterns when strong winds are included. Without early feedback, galaxies grow too massive too quickly, and the intergalactic medium remains too pristine. Including winds spreads energy and metals broadly, matching observed metallicity levels and galaxy masses. Early galactic winds therefore operated as organizing forces. They redistributed matter and energy across the cosmic web, moderated galaxy growth, and shaped the environments in which later galaxies formed. Their influence extended well beyond individual halos, affecting the pace and pattern of structure formation itself. As the universe expanded and galaxies grew more massive, winds gradually weakened in relative strength. Deeper gravitational wells confined gas more effectively. Star formations spread over longer time scales. Yet the imprint of early winds remained, encoded in metallicity patterns, galaxy demographics, and the structure of the cosmic web. During cosmic dawn, galaxies breathed forcefully and often. Their winds carved paths through surrounding space, enriched vast regions, and set the initial conditions for billions of years of cosmic evolution that followed. Modern astronomy reveals galactic winds through their interaction with light. Gas moving at high speed imprints subtle signatures on radiation passing through it, emits across a wide range of wavelengths, and reshapes the diffuse environments around galaxies. By combining these signals, astronomers reconstruct winds across distance, time, and physical scale. One of the most powerful tools for detecting galactic winds comes from absorption line spectroscopy. When light from stars or distant background sources passes through outflowing gas, specific wavelengths are absorbed by atoms and ions along the line of sight. These absorption lines appear shifted toward shorter wavelengths when gas moves toward the observer, directly encoding velocity. In star-forming galaxies, absorption lines from elements such as sodium, magnesium, silicon, carbon, and oxygen often show systematic blue shifts. The magnitude of these shifts indicates gas moving outward at hundreds to thousands of kilometers per second. Because absorption traces material along the line of sight regardless of brightness, this method reveals winds even when the gas itself emits little light. Background quasars provide especially sensitive probes. When a quasar's light passes near a foreground galaxy, absorption features reveal gas in that galaxy's halo. By sampling many such sightlines, astronomers map the distribution, velocity, and chemical composition of wind-driven material far from galactic disks. These observations show metal-enriched gas extending tens to hundreds of thousands of light-years outward. Emission line imaging provides a complementary view. Ionized gas emits characteristic spectral lines when electrons recombine with ions or transition between energy levels. Optical emission from hydrogen and oxygen traces warm, ionized gas lifted above galactic disks. These emissions often form filamentary structures aligned with outflows, revealing the geometry of winds directly. In nearby starburst galaxies, emission line maps display large-scale bipolar structures extending well beyond the stellar disk. Velocity measurements across these regions reveal coherent expansion rather than random turbulence. The alignment of these structures with regions of intense star formation links them directly to feedback-driven outflows. Infrared observations add another layer. Dust grains heated by stellar radiation emit strongly at infrared wavelengths. Extended infrared halos around star-forming galaxies indicate dust carried outward by winds. Because dust couples efficiently to gas and radiation, its distribution traces wind pathways even where gas emission remains faint. X-ray observations probe the hottest phase of galactic winds. Hot plasma at millions of degrees emits X-rays through thermal bremsstrahlung and line emission from highly ionized metals. Space-based X-ray telescopes reveal bubbles, cavities, and extended halos of hot gas surrounding star-forming and active galaxies. These X-ray structures often align with optical and infrared outflows, indicating a shared origin. The size and temperature of X-ray bubbles constrain the total energy injected by feedback and the efficiency with which it couples to gas. In many galaxies, X-ray halos extend tens of thousands of light-years, demonstrating that winds remain hot and energetic far from their launch sites. Radio observations trace yet another component: cosmic rays and magnetic fields. Synchrotron radiation emitted by relativistic electrons spiraling along magnetic field lines reveals extended radio halos above galactic disks. The scale height of this emission provides a measure of how far cosmic rays travel before losing energy, offering indirect insight into wind transport. Polarization measurements show ordered magnetic fields aligned with outflow directions. These observations confirm that magnetic fields remain structured and dynamically relevant within winds, guiding particle transport and influencing gas dynamics over large distances. By combining these wavelength regimes, astronomers reconstruct the multi-phase structure of winds observationally. Hot X-ray emitting plasma fills most of the volume. Warm ionized gas outlines interfaces and filaments. Neutral and molecular gas appears in absorption and radio emission. Dust traces momentum transfer and radiation coupling. Time adds another dimension. Observations at different redshifts allow astronomers to study winds across cosmic history. Distant galaxies observed as they appeared billions of years ago often display stronger outflow signatures relative to their mass than nearby galaxies. This trend reflects higher star formation rates and shallower gravitational potentials in the past. Spectroscopic surveys of distant galaxies reveal widespread outflows even in modest systems. Absorption features indicate high-velocity gas common during earlier epochs. These data connect present-day wind physics to the vigorous feedback that shaped early galaxy evolution. Large surveys enable statistical approaches. By observing thousands of galaxies, astronomers correlate wind strength with star formation rate, galaxy mass, morphology, and environment. These correlations reveal that winds strengthen with increasing star formation intensity and weaken as galaxies grow more massive. Integral field spectroscopy has transformed wind studies further. This technique captures spectra across entire galaxies simultaneously, producing spatially resolved velocity and chemical maps. These maps reveal how winds launch, accelerate, and interact with surrounding gas in real time, rather than as one-dimensional averages. Numerical modelling plays a crucial role in interpreting observations. Simulations generate synthetic spectra and emission maps that can be compared directly to data. Matching observed line profiles, temperatures, and spatial structures constrains feedback efficiency, mass loading, and energy transport. Uncertainties remain. Measuring total mass loss proves challenging because different phases dominate different diagnostics. Hot gas carries energy but little mass. Cold gas carries mass but emits weakly. Dust complicates interpretation by absorbing and re-emitting radiation. Observations therefore capture pieces of a complex whole. Despite these challenges, the convergence of evidence across wavelengths paints a consistent picture. Galactic winds operate in diverse systems, persist over long timescales, and influence gas far beyond stellar disks. They appear in nearby galaxies in exquisite detail and in distant galaxies as subtle but widespread signatures. Modern observatories extend this reach continuously. Improved sensitivity, spectral resolution, and spatial coverage allow astronomers to probe fainter gas, map larger halos, and trace winds deeper into cosmic time. Each new dataset refines understanding of how galaxies exchange matter and energy with their surroundings. Through absorption lines, emission halos, X-ray bubbles, and radio structures, galactic winds reveal themselves not as rare anomalies, but as common features of galaxy evolution. Observations across the electromagnetic spectrum transform these vast, diffuse flows into measurable phenomena, connecting theoretical models to the observable universe and anchoring the study of galactic winds firmly in empirical evidence. Galactic winds evolve as galaxies themselves change. Their strength, structure, and reach depend on how much energy galaxies continue to inject into their gas and how effectively gravity confines that energy. As star formation slows and central activity declines, winds adjust gradually, transitioning from dominant drivers of motion to weaker circulatory flows embedded within aging systems. In young and actively star-forming galaxies, energy injection remains continuous. Massive stars form frequently. Supernova rates stay high. Black holes accrete intermittently. Under these conditions, winds remain sustained, replenished, and dynamically important. Gas lifts easily into halos, cycles rapidly, and in some cases, escapes entirely. As galaxies age, this balance shifts. Gas reservoirs decline over time. Star formation consumes available fuel while winds remove or redistribute it. Without fresh inflow at sufficient rates, star formation slows. The population of massive stars decreases, radiation pressure weakens, stellar winds diminish, supernova explosions become less frequent and more isolated in time. With reduced energy input, pressure gradients flatten. Hot gas still exists, but its volume shrinks and its temperature drops more quickly through radiative cooling. Winds lose coherence. Instead of large-scale outflows, galaxies develop localized circulation and gentle fountains confined closer to the disk. This transition occurs gradually rather than abruptly. Many galaxies pass through extended intermediate phases where modest winds coexist with declining star formation. Gas continues to move, but with reduced velocity and reach. Material lifted into halos falls back more readily. Escape becomes rare, except during episodic bursts of activity. Galaxy mass plays a defining role in this evolution. Massive galaxies develop deep gravitational wells that confine gas efficiently. As stellar feedback weakens, gravity dominates. Hot halos remain, but outflows struggle to propagate far. Gas settles into long-lived reservoirs that cool slowly and circulate without escaping. In lower mass galaxies, the outcome differs. Early winds often remove large fractions of gas permanently. Over time, these systems become gas-poor. Star formation declines sharply or ceases altogether. With little remaining fuel, winds fade not because gravity strengthens, but because energy sources vanish. Black hole activity introduces another layer. In massive galaxies, black holes often reach peak accretion after major star formation episodes. Their outflows heat surrounding gas and prevent efficient cooling. This maintenance feedback keeps halos hot and stable, suppressing renewed star formation without driving dramatic winds. Gas remains present but dynamically quiet. The interstellar medium responds accordingly. Turbulence decays, magnetic fields relax, cosmic ray populations thin, gas density distributions smooth out. Star-forming regions become rare and isolated. Instead of large cavities and chimneys, galaxies develop stable, stratified atmospheres. From the outside, these galaxies appear calm. Optical images show smooth stellar distributions with little dust or gas. X-ray observations reveal extended, faint halos of hot plasma lingering as relics of past activity. Radio emission weakens as cosmic ray production declines. Despite this quiet appearance, circulation does not cease entirely. Gas continues moving slowly within halos. Cooling flows form weak streams. Small amounts of gas accrete from the surrounding environment. Stellar mass loss from aging stars replenishes the interstellar medium at low levels. These processes maintain a slow, steady exchange rather than active breathing. On cosmic timescales, this transition alters how galaxies contribute to their surroundings. Young galaxies export energy and metals efficiently. Older galaxies retain what remains. Chemical enrichment of the intergalactic medium slows. New enrichment occurs primarily in regions where star formation persists. The cumulative effect shapes cosmic evolution. Early winds distribute heavy elements widely, preconditioning gas for future structure formation. Later, declining winds preserve established structures rather than reshaping them. The universe shifts from an era of rapid redistribution to one of gradual settling. Large-scale environments reflect this change. Galaxy clusters retain hot, enriched gas that cools inefficiently. Filaments contain material processed long ago. The rate at which galaxies modify their surroundings decreases as the dominant sources of feedback weaken. Simulations capture this progression clearly. Early epochs show vigorous outflows and frequent gas cycling. Intermediate epochs feature mixed behavior, with fountains dominating over escape. Late epochs show confined halos and reduced circulation. Galaxy populations evolve accordingly, with fewer actively star-forming systems over time. The long-term fate of galactic winds therefore lies in transformation rather than disappearance. Winds do not simply stop, they weaken, shorten, and change character. What once expelled gas into intergalactic space becomes a mechanism for internal balance and slow redistribution. In aging galaxies, the breathing continues quietly. Gas drifts rather than surges. Energy dissipates rather than accumulates. Motion persists without dramatic consequence. Over billions of years, this subtle circulation governs how galaxies settle into stable configurations, carrying forward the imprint of earlier, more active phases without reawakening them. Across cosmic history, galactic winds trace this arc, from forceful drivers of growth and change to subdued participants in long-term equilibrium, shaping how galaxies mature, how environments stabilize, and how the universe transitions from its turbulent youth into a more quiescent state.